Welcome to Lab 1 for Introductory Physics. The topic is constant velocity motion. In this lab, I will test Newton's second law and see if I can predict the motion of an object moving in one direction at the same speed. The object I chose to study was an empty peanut butter jar with a lid diameter of about 3 inches or 0.078 meters in SI units. In order to assist me with my study of an object with constant velocity motion, I'm going to use Newton's second law to predict future motion. And in this formula, v sub f is the final velocity, v sub I is the initial velocity, F net is the net force, or total pushes and pulls, m is the mass, and delta t is the change in time. To create my computational models, I used Tracker, VIDLE, and a spreadsheet program. I noticed if I used too much force, the jar would not roll in a straight line, so it took a few tries. Here now is my Tracker data. I imported my video into Tracker, and you can see my center of mass indicated in the video, and you can also see a Cartesian graph in the upper right and a table of data in the bottom right. The graph and the table show the position of the jar at a given time. Now I need to calculate the initial velocity of the peanut butter jar. The velocity is measured in meters per second and is used in Newton's second law so I can predict the motion. To calculate it, take the change in position and divide it by the change in time. I get my time and position data from the table in Tracker. The first column shows the time and the other columns show position. To put our position in proper notation, we include the x, y, and z coordinates. Since the jar is only moving on the x-axis, I put in 0 values for y and z. My peanut butter jar is moving in a positive direction on the x-axis. When I calculate it out, I divide 0.01 divided by 0.33, and I round off my result to 0.303. Now I'm going to use a computer model to calculate Newton's second law. I open VIDLE and enter my initial velocity, 0.303 meters per second. Because my jar only moves along the x-axis, I enter 0 for y and z coordinates. I enter the mass of my jar in kilograms. Here I edited the Python code to match the Newton's second law formula I'm using. The jar's final velocity equals initial velocity plus net force divided by mass times delta t. Now I change the line of Python code to match the position update formula. The final position equals the initial position plus velocity times delta t. To define F net, I want to assume no net forces, so I set the net force to 0 to get the velocity constant. To export my computer model results in a usable format, I uncomment certain lines of code so the results will be output into CSV format. The data can then be analyzed in a spreadsheet program. I run the Python code in VIDLE and I see a simple model of my jar's movement in the positive direction along the x-axis. I also see a graph showing the jar's position from 0 seconds to about 1.5 seconds. Here is the resulting CSV data from VIDLE. These are the model positions based on Newton's second law with my jar's mass and initial velocity plugged into the formula. For my actual experiment, the data can be found in the Tracker table. Now I'm going to compare my experimental data with the model data. In Google Sheet, I put my actual experimental data into the spreadsheet by copying and pasting it from Tracker. Then I copied and pasted the model data to predict my jar's motion. This data came from the CSV file generated by VIDLE. I plotted a line chart to compare my experimental actual data with the model data. The experimental actual positions of the jar are shown by the blue dots connected by a line. The model position, based on Newton's second law, is shown by the red line. As you can see, the model data and the actual experimental data do not overlap, except for the first 2 points. The first 2 points match because I used those points to calculate the jar's initial velocity for Newton's second law formula. However, the jar's actual velocity is slower than the predicted velocity. That makes sense because my system, the jar, was being acted upon by its surroundings, namely the Earth's gravitational pull and the friction from the air and the floor. How would my results change if I were to flip the axes? Here is a simplified model of my graph which shows the position versus time of my peanut butter jar. Notice that the time and position both move in a positive direction. If I flip my graph 90 degrees, the data hasn't changed. The representation looks different, but the time and position are still in the positive direction, as denoted by the plus signs. To sum up, my actual jar was met with net forces, and Newton's second law assumes zero net forces. Therefore, my jar's velocity was slower than the predicted velocity.